The definite integral. The integral concept is associated with the concept of area, and the basic problem in integral calculus is finding the area under a curve. So in this video, we start with the problem of finding the areas as a limit of a sum. If you need an introduction to sigma notation, watch the video shown in the upper right corner of the screen for a brief introduction to sigma notation. Thanks in advance for watching this video. If you like this video, don't forget to like and subscribe to the channel and activate the bell. It is very important for the continuity of this channel. When a plane figure is bounded by straight lines, it is easy to calculate its area. For a rectangle, the area is defined as the product of the length and the width. The area of a triangle is half the base times the height. The area of a polygon is found by dividing it into triangles and adding the areas of the triangles. However, it is not so easy to find the area of a region with curved lines. To start, we assume f of x be a continuous function defined on the closed interval ab. For the present, assume that all the values taken by the function are positive, so that the graph of the function is a curve above the x-axis. Our goal is to compute the area of the region between this curve and the x-axis. At the first glance, we cannot do this exactly. However, we can estimate the area. One way to do this would be to approximate the area with rectangles. The area of a rectangle is equal to height times width. The width of each rectangle is delta x. And to find the height of each rectangle, we choose a sample point c sub k and evaluate the function at that point. The value f of c sub k determines the height of a rectangle. Then we can find the area of each of these rectangles, add them up, and this will be an approximation to the area under the graph. Using more rectangles can increase the accuracy of the approximation. In short, the more the number of rectangles, the more accurate the area is. These sorts of approximations are called Riemann sums. Now let's focus on understanding the Riemann sums and how they lead us to the definition of the definite integral, which calculates the exact value of the area. Let's take a look at the non-negative function f of x that is continuous within the closed interval ab. To make a Riemann sum, we must choose how we are going to make our rectangles. Three different approaches for computing the Riemann sum estimate for a function f of x are shown below. One possible choice is to make our rectangles touch the curve with their top left corners. This is called a left Riemann sum. We approximate the area using rectangles, usually of equal width, where the height of each rectangle is equal to the value of the function at the left endpoint of its base. Another choice is to make our rectangles touch the curve with their top right corners. This is a right Riemann sum. In a right Riemann sum, the height of each rectangle is equal to the value of the function at the right endpoint of its base. In a midpoint Riemann sum, the height of each rectangle is equal to the value of the function at the midpoint of its base. Now let's calculate the area under the graph using the Riemann sum for each case. If the width of each rectangle is delta x, we can multiply each function value by delta x and these products are added to determine their sum. We can use sigma notation. Pay attention. Let's solve an example to make the theory clearer. Approximate the area between the function and the x-axis from 0 to 1 with 5 uniform subdivisions. The number of subdivisions is simply the number of rectangles we use, so we will use 5 rectangles. Establish the value of delta x. In other words, the width of each of the 5 rectangles. The full interval from 0 to 1 has width 1 minus 0, so each subinterval has width x equals 1 minus 0 over 5. The width of each of the 5 rectangles is 0.2. The next step is to find the end points of the rectangles. Recall that we can do this in 3 different ways. We now use the definition of the left-hand Riemann sum. Each rectangle has a width of 0.2, and the height of each is given by the height of the function at the rectangle's left edge. Adding the areas gives us 0.76. Now let's estimate the same area under the graph at which each rectangle is drawn so that its right upper corner touches the curve. The heights of the 5 rectangles are given by the function values at their right edges. Adding the areas gives us 0.56. A third way to approximate areas with rectangles is to make each rectangle cross the curve at the midpoint of its top side. The height of each is given by the function value at the midpoint of their top side. Adding the areas gives us 0.67. The first approximation gives an overestimate of the total area under the curve because of the gaps between the rectangles and the curve. The second approximation gives an underestimate of the total area under the curve. The midpoint sum is a much better estimate of area than either a left or a right sum, because the part of each rectangle that's above the curve is about the same size as the gap between the rectangle and the curve. So these two errors roughly cancel out each other. As we have seen, to find the area under a curve, we divide the area into rectangles and sum them up. The more rectangles we have, the better the approximation is. So we define the exact area under the curve as a limit of the Riemann sums when the number of the rectangles is infinite. But before using limits, we have to define some irrelevant terminology. We begin with a function f defined on a closed interval, ab. The set p from x sub 0 to x sub n, where x sub 0 is equal to a, and x sub n is equal to b, is called a partition of interval ab, since p divides the interval from a to b into n closed subintervals of equal width, delta x, as follows. They don't need to be of equal width, but if they are, the calculations are easier. The end points of each subinterval are given as follows. In each subinterval, we select some point. The point chosen is called c sub k, and then we find its function value, f of c sub k. This point, c sub k, will define the height of the rectangle in each subinterval. Note as well that these points do not have to occur at the same point in each subinterval. However, they are usually the left endpoint, right endpoint, or the midpoint of the interval. On each subinterval, we stand a vertical rectangle that stretches from the x-axis to touch the curve at the point c sub k. On each interval, we form the product f of c sub k times delta x. These n products are added to determine their sum. This sum is called a Riemann sum of f of x on AB. Left Riemann sum, right Riemann sum, and the midpoint Riemann sum are given as follows. If the number of subintervals increases without bound, in short, when the number of a rectangle approaches infinite, then the length of each subinterval approaches 0. This limit of a Riemann sum is the exact area under a curve y equals f of x. X belongs to the interval AB. We give this type of limit a special name and notation. Let f of x be continuous on AB and consider the partition x sub k. We divide the interval into n subintervals of equal width, delta x. For any sample points c sub k, the limit of a Riemann sum is a fixed number called definite integral of f from a to b, denoted by, provided that this limit exists and gives the same value for all possible choices of sample points. The number a is the lower limit of integration, and the number b is the upper limit of integration. Let's start with a very simple example. Evaluating the integral of 3 from 0 to 2 is the same as finding the area under the curve in the given interval. Since we have a constant function, it's easier to use geometry to calculate the area. As we can see from the graph, the area under the curve is a rectangle. So let's calculate the area with the formula for the area of the rectangle. The area is equal to 6. Now, let's evaluate this integral by definition as the limit of a Riemann sum. We find the value of delta x, and then we use the definition. We replace f of x with 3 and delta x with 2 over n. Before calculating the limit, we have to evaluate the summation. Now we can calculate the limit. Let's look at the next example. Remember that evaluating the integral of x from 1 to 3 is the same as finding the area under the curve in the given interval. Since we have a linear function, it's still easy to use geometry to calculate the area. As we can see from the graph, the area under the curve is a trapezoid. So let's calculate the area by the formula for the area of the trapezoid. The area is equal to 4. Now let's evaluate this integral by definition as the limit of a Riemann sum. We find the value of delta x and then choose a partition. Let's solve this example step by step using the 3 partition modes. First, let's solve the integral using the left Riemann sum. We find the value of delta x using the upper and lower limits of integration, and c sub k as the left endpoint of the partition. We now write the definition of definite integral as the limit of the Riemann sum. We replace c sub k with the expression above and delta x with 2 over n. Before calculating the limit, we have to evaluate the summation. Evaluating the summation is usually the hardest part. After applying the summation formulas and simplifying the n's, we can calculate the limit. Pay attention. Now let's evaluate this integral by definition using the right Riemann sum. We always start by finding the value of delta x using the upper and lower limits of integration, because we use the value of delta x for the partition expression in the Riemann sum. The next step is taking c sub k as the right endpoint of the partition. We write the definition of definite integral as the limit of the Riemann sum. We replace c sub k with the expression above and delta x with 2 over n. Before calculating the limit, we have to evaluate the summation. After applying the summation formulas and simplifying the n's, we can calculate the limit. Pay attention. Now let's evaluate this integral by definition using the midpoint Riemann sum. The calculations are similar to what we have just done, but will still be done in detail. We start by finding the value of delta x, and then we take c sub k as the midpoint. We write the definition of definite integral as the limit of the Riemann sum. We replace c sub k with the expression above and delta x with 2 over n. Now we proceed in a similar way as we did before. As we can see, the limit gives the same value for all possible choices of sample points, c sub k. So we generally use one of the above methods as it makes algebra simpler. In calculus, limits are used to define basic quantities that otherwise would not have a precise meaning. You should recall we first learned of derivatives through limits and then learned rules that made the process simpler. We just learned a way to evaluate a definite integral using limits. In the next video, we will see how the fundamental theorem of calculus makes the process simpler. The next two examples are also solved in detail, but you should try to solve them yourself and then check the answers.